In this screencast, I'm going to be cleaning up a couple of things that, again, tying together things you already know in many cases, but I hope helping you see things in a slightly more complete way. But you'll you will recognize a lot of this as things you have heard before in various contexts. This first part's very brief about types of solids. So the first thing you should know is that not all solids are crystalline. So a crystalline solid has a very regular arrangement. Remember we talked about lattice. Lattice is a regular arrangement. It doesn't have to be square, but it is regular and repeating. Table salt's like that. A lot of other crystals are like that. Funny thing about crystals is they really break very easily. They're brittle. Amorphous solids just means they don't have any shape that's predictable. They don't have a regular repeating structure. Glass is an amorphous solid. Couple of very quick things about crystalline solids. I don't want you to stress too much about this or worry too much. I will make a clear point when I think there's something you need to know. A lot of this is just for context. So the lattice, as we talked about, is a three-dimensional system of points, and there's a lot of details on the names of that, how that works. And I don't really need you to memorize a lot of that, but something like the unit cell is just the smallest repeating unit. Don't need to really remember that, but get the idea that if there is a regular repeating structure, then the smallest repeating unit is going to be either one molecule, but it may be groups of molecules. Don't worry about cubic or face-centered. These are all just ideas I want you to know are out there. Okay, ionic solid. Now here's something I do want you to think about. So in an ionic solid, you've always got ions at the points of the lattice. So if you think about a lattice as sort of a repeating structure, you would have a sodium or a chloride at each point of the cubic squares. A molecular solid, however, is going to have discrete covalent bonded molecules at its lattice points, so like sugar or water. And here's just a couple of examples. So if you take a look at this here we have the larger chlorides and the small sodium pluses alternating, occupying points of the lattice. Here, water molecules linking through hydrogen bonds to each other, forming ice in a regular repeating structure. And you can see ice is not cubic. The one I want to draw your attention to for a little bit over here is diamond. Now, diamond is unusual in that it is a covalent crystal. Basically, you can think of it as one large molecule. All the atoms of carbon are linked to four other atoms of carbon in the overall structure. If you're doing some reading online or looking at some videos, you might hear a discussion of how intermolecular forces affect melting point. And we've talked about it. Sodium chloride melts at a much higher point than water. Water melts at a higher point than a lot of small things, and that comes down to the strengths of the bonds. The bonds between water molecules are hydrogen bonds, which are strong as intermolecular interactions go. Ionic interactions are much stronger, and so sodium chloride melts at a much higher temperature. Covalent bonds are a lot stronger than ionic interactions. You will run across places that dispute that. But consider for a moment, when you melt sugar, you're not melting or breaking the covalent bonds that hold the sugar molecule together. You're breaking the weak interactions, hydrogen bonds, that hold one sugar molecule to another. The equivalent would be trying to melt a diamond. Well, diamonds don't even melt. You have to get to really high pressures. But nevertheless, you will run into people who will suggest that, well, covalent compounds melt at lower temperatures, and that suggests that they have weaker interactions. Well, they have weaker interactions between the molecules, but the interactions holding the molecule together, the covalent bonds, are actually much stronger than ionic interactions, and that's given by the evidence for that is given by things like diamond or other molecular crystals. Network solids don't melt. Okay, they have extremely high melting points or don't melt at all. Network solids are composed of strong covalent directional bonds, and they're basically you can think of them as a giant molecule. A whole diamond is pretty much one molecule. They're very poor conductors of heat or electricity. Why would they be poor conductors of heat? Well, there's not a lot of what is heat? It's average kinetic energy. When something gets heated up, even if it's a solid, you're looking at the movement of the molecules, right? So even if it's a solid, you're looking at an increased movement of the molecules. Covalent bonds don't allow for a lot of increase in movement of the molecules. So it's not very easy to heat up a diamond. Often they're carbon and silicon based, and that's because carbon and silicon, you may take a look at them on the periodic table, both of them have the 4 valence electron structure and can make networks among other atoms. So here's 2 network solids. Well, diamond is a true network solid. Graphite is a network in sheets, but then the sheets interact with each other through fairly weak interactions. That enables them to slide along. Graphite actually makes a very good lubricant because 2 graphite sheets can slide relative to each other. But you may have run into things or heard of things such as carbon fibers and graphene, which are sheets of very strong single molecular layer sheets of carbon networks. Really, really wonderful materials for building strong structures. Okay, so this opens up a new category, vapor pressure. Before I move on to that, I want to recap a few things that you should know. You should know that solids are not all crystalline. Some solids are amorphous. They don't have a regular repeating structure. You should know that when you're melting a crystal, generally you are breaking intermolecular associations. You are generally not breaking the molecular bonds that are holding a molecule together. So when you melt sugar, you're not breaking the covalent bonds. You're breaking the weak hydrogen bonds between the molecules. When you melt water, you're not breaking the bonds between the hydrogen and oxygen holding the water molecule as a molecule. You are breaking the relatively weak hydrogen bonds between water molecules. The exception to this is when you get to something like a diamond that is a network of covalent bonds, and they just don't melt. Covalent bonds are very, very strong.